January 17th, 1940. Wright Field, Dayton, Ohio. The air inside Hangar B smelled of burnt oil and cold metal. Snow drifted through the cracks in the corrugated steel walls, settling on blueprints spread across a wooden workbench. Outside, the temperature had dropped to 12 degrees below zero, but inside, beneath a single flickering work lamp, a man's hands moved with the precision of a surgeon. His name was Samuel Heron, though the other engineers had begun calling him something else: the mad Irishman, the lunatic, the man who doesn't sleep. He didn't care. His fingers traced the edge of a cylinder head, feeling for imperfections invisible to the naked eye. Around him, the hum of a nation not yet at war continued, oblivious. But Heron knew something they didn't. He knew that wars were won not by generals or politicians, but by the invisible margins of engineering, by fractions of horsepower, by degrees of temperature tolerance, by the willingness of one man to ignore every order he'd been given. The engine block before him was not supposed to exist. It violated 3 separate directives from the Army Air Corps. It exceeded the weight limitations set by the procurement office. It used materials that had been explicitly forbidden. And yet, in the dim light of that January morning, as frost formed on the windows and the rest of Wright Field slept, Samuel Heron tightened the final bolt on what would become the most powerful aircraft engine ever conceived. An engine that would carry American bombers across oceans. An engine that would rewrite the mathematics of aerial warfare. An engine built entirely in defiance of the men who were supposed to know better. He stepped back, wiping grease from his hands onto a rag that had long since given up absorbing anything. The engine sat there, silent and massive, a monument to obsession. In 6 months, commanders in Berlin and Tokyo would begin receiving reports that made no sense. American aircraft flying at altitudes that should have been impossible, carrying bomb loads that violated every known principle of aerodynamics, operating with a reliability that seemed almost supernatural. They would search for explanations in captured technical manuals, in interrogated pilots, in the wreckage of shot-down planes. But the real answer would remain hidden in this moment, in this freezing hangar. In the stubborn refusal of one man to accept the limitations that others insisted were absolute. Heron lit a cigarette, his breath visible in the cold air. Tomorrow he would face the tribunal. Tomorrow they would demand explanations for the unauthorized expenditures, the diverted materials, the countless regulations he had simply ignored. Tomorrow they would threaten court-martial, discharge, disgrace. But tonight, the engine existed, and that was enough to understand why Samuel Heron stood in that hangar, why he had risked everything to build something he had been explicitly ordered not to build. One must first understand the peculiar crisis facing American aviation in the winter of 1939. The war in Europe had begun 4 months earlier. Poland had fallen in weeks. France cowered behind the Maginot Line, and American military planners, watching from across the Atlantic, had begun to perform calculations that yielded increasingly disturbing results. The Boeing B-17, America's newest heavy bomber, could carry 4,800 pounds of bombs across a range of roughly 2,000 miles. On paper, this seemed adequate, but the calculations revealed a darker truth. To reach Berlin from England and return safely, the B-17 would need to carry additional fuel, which meant reducing bomb load. To defend against fighter interception, it would need more ammunition, heavier armor, more weight. To operate effectively at the altitudes necessary to avoid flak, it would need pressurization systems, oxygen equipment, still more weight. By the time military planners finished adding everything necessary for actual combat operations, the B-17's theoretical capabilities had evaporated into mathematical impossibility. The problem was the engine. The Wright R-1820 Cyclone that powered early B-17s produced 1,200 horsepower. Impressive for its time, but insufficient for the demands of strategic bombing. American engineers had been working on more powerful alternatives, But they had been working conservatively, incrementally, following the established wisdom that engine development was a process of careful, measured progress. Each new design added perhaps 50 horsepower, perhaps 100. At this rate, the engine needed to fight the coming war would be ready sometime around 1945. Samuel Heron believed they were thinking about the problem wrong. Born in Ireland in 1891, Heron had spent his youth not in universities, but in workshops, learning engineering the old way, by touch, by failure, by the accumulated wisdom of men who built things with their hands. He had come to America in 1921, bringing with him theories about engine cooling that most American engineers considered eccentric at best. He spoke with an accent that made procurement officers suspicious. He had a habit of ignoring chains of command. He drew sketches on napkins during official meetings. He was, in the words of one Army Air Corps memo, brilliant but difficult to manage. By 1939, Heron had been working at Wright Field for nearly a decade, long enough to understand how the military bureaucracy functioned, long enough to know that revolutionary designs died not from technical impossibility, but from administrative caution. He had watched promising projects suffocate under layers of review committees, safety protocols, and procurement regulations designed to prevent failure, but that also prevented innovation. He had learned that if you wanted to build something truly new, something that broke the existing paradigms, you could not ask permission. You could only build it and present them with an accomplished fact. The engine that Heron conceived that winter was not an incremental improvement. It was a fundamental reimagining. Where existing engines used air cooling, Heron proposed liquid cooling with ethylene glycol, a substance most engineers considered too volatile for aircraft use. Where existing engines topped out at around 1,500 horsepower, Heron calculated that his design could produce 2,000, perhaps 2,200. Where existing engines required elaborate maintenance schedules, Heron's design used simpler, more robust components that could be serviced by mechanics with basic training. He presented his preliminary designs to the procurement office in November 1939. They rejected them in December. Too radical, they said. Too risky. The materials were unproven. The cooling system was too complex. The entire concept violated established principles of aircraft engine design. They suggested he submit a revised proposal in 6 months, something more conventional, something that wouldn't frighten the oversight committees. Heron nodded politely during the meeting. He thanked them for their time, and then he returned to Hangar B and began building the engine anyway. The German engineers believed they had achieved perfection. In the summer of 1940, as the Luftwaffe prepared for the aerial assault on Britain, German technical journals brimmed with confidence about the superiority of their aircraft engines. The Daimler-Benz DB 601, which powered the Messerschmitt Bf 109, represented the culmination of German engineering philosophy, precision manufacturing, careful optimization, systematic refinement of proven concepts. It produced 175 horsepower, more than adequate for the lightweight fighters Germany had designed. German pilots expected to dominate the skies through superior tactics and superior engineering. What they expected was air combat on their terms, at altitudes where their engines performed optimally, against opponents who followed conventional design philosophies. What they experienced beginning in 1941 was something else entirely. American bombers began appearing at altitudes the German fighters struggled to reach. They carried bomb loads that German intelligence insisted were impossible given the aircraft's known specifications. They absorbed damage that should have been catastrophic, flak strikes that punctured fuel tanks, fighter attacks that shredded control surfaces, and continued flying. Most baffling of all, they maintained formation integrity with a mechanical reliability that German commanders found incomprehensible. Luftwaffe after-action reports from 1942 and 1943 are filled with frustrated notations about American aircraft that should have failed but didn't. that exceeded performance specifications without explanation. The Japanese experience mirrored Germany's. Zero fighter pilots, accustomed to dominating Pacific skies through superior maneuverability and climb rate, found themselves facing American aircraft that simply climbed above them and stayed there. Japanese technical intelligence units captured intact American engines and disassembled them, searching for the secret. They found components that seemed crude by Japanese standards, less precise machining, simpler assembly methods. And yet these engines produced more power, ran longer between failures, and tolerated combat damage that would have destroyed Japanese engines. The mathematical calculations didn't make sense. The Americans were violating fundamental principles. What neither German nor Japanese intelligence understood was that they were encountering not just a better engine, but a different philosophy of engineering itself. Samuel Heron had not built a more precise version of existing engines. He had built an engine designed around different assumptions. Assumptions about mass production, about field maintenance, about the messy realities of combat operations versus the clean abstractions of laboratory testing. The engine he had created in that freezing hangar in January 1940 was the Wright R-3350 duplex Cyclone, and by 1943 it was powering the B-29 Superfortress, an aircraft so far beyond existing capabilities that it seemed to belong to a different era of technology. But in January 1940, none of this had happened yet. In January 1940, there was only a man in a hangar working by lamplight, building something he had been ordered not to build. The documented evidence of Heron's unauthorized work survives in scattered fragments. A requisition form dated January 23, 1940, requesting specialized steel alloys for experimental purposes, signed with the name of a supervisor who later claimed he never authorized it. A work order from the machine shop, stamped Priority Confidential, that directed technicians to manufacture cylinder heads to specifications that matched no approved design. A memo from the supply sergeant, noting irregular withdrawals of ethylene glycol from base stores. By February, rumors had begun circulating. Engineers working on approved projects would arrive at the workshops to find equipment missing, materials diverted, machinists occupied with components that belonged to no official program. Questions were asked. Heron deflected them with technical jargon and vague references to consultative work. He had a genius for bureaucratic camouflage, for making his unauthorized project appear to be some obscure extension of legitimate research. He submitted progress reports on approved projects while secretly documenting the engine's development in personal notebooks. Kept in his locker, the test data from those notebooks reveals the magnitude of what he was attempting. On March 3, 1940, the first cylinder assembly was mounted on a test stand and fired. It ran for 17 seconds before overheating and seizing. On March 9th, a modified version ran for 4 minutes. On March 15th, 6 minutes. The temperatures were too high. The cooling system wasn't adequate. Heron spent 2 weeks redesigning the coolant channels, working through the night, sleeping in 2-hour intervals on a cot in the hangar. On April 2nd, the revised assembly ran for 33 minutes before a valve failure. On April 10th, 2 hours. On April 18th, 4 hours, producing 1,147 horsepower, more than any aircraft engine in American inventory. The breakthrough came not from theory, but from intuition. Existing engines used cooling fins that dissipated heat through air circulation. Heron had designed liquid cooling channels that ran through the cylinder walls, but the initial configurations created hotspots where coolant flow was insufficient. Traditional engineering would have suggested elaborate computational fluid dynamics studies, weeks of analysis. Heron instead walked to the base cafeteria, ordered coffee, and watched how the liquid swirled when he stirred it. He returned to the hangar and redesigned the coolant channels with curved baffles that induced turbulent flow, forcing the liquid to mix continuously rather than flowing in straight lines. The modification violated every principle of efficient fluid dynamics. It increased pumping resistance and reduced overall flow rate, but it eliminated the hotspots. On May 7, 1940, the complete engine, 18 cylinders, 2 rows of 9, configured in a radial pattern, ran continuously for 12 hours at 2,000 horsepower. Heron stood beside it, monitoring temperatures, listening to the rhythm of combustion, feeling the vibrations through the test stand's steel frame. At hour 11, a small crowd had gathered, other engineers, mechanics, pilots who had heard rumors of something extraordinary happening in Hangar B. They watched in silence as the engine ran, hour after hour, producing power levels that shouldn't have been possible, operating at temperatures that should have caused catastrophic failure, maintaining stability that defied conventional engineering wisdom. At hour 12, Heron shut it down. The sudden silence felt heavy, profound. Someone started clapping. Others joined. Heron didn't acknowledge them. He was already making notes, documenting measurements, identifying modifications for the next test. He knew what they didn't, that building the engine was only half the battle. The other half was convincing the men who made decisions that what they were seeing was real. The tribunal convened on May 15, 1940, in a conference room that smelled of furniture polish and stale coffee. 5 officers sat behind a long table, their uniforms pressed, their expressions ranging from skepticism to outright hostility. The charges were read: unauthorized expenditure of military resources, violation of procurement protocols, insubordination, willful disregard of direct orders. The potential consequences were enumerated: court-martial, discharge, possible criminal charges for theft of government property. Heron stood before them in oil-stained work clothes, a leather folder under his arm containing test data. He had not shaved in 3 days. He looked like what he was, a mechanic who had been living in a workshop, obsessed with the machine. The lead officer, a colonel named Henderson, who had spent his career managing budgets and schedules, opened the questioning. "Mr. Heron, do you understand the seriousness of these charges?" "I do. And do you deny that you diverted materials, equipment, and personnel to an unauthorized project?" "I don't deny it." "Then perhaps you can explain why we shouldn't immediately remove you from this facility and initiate proceedings for court-martial." Heron opened the folder. He extracted a single sheet of paper and placed it on the table in front of Henderson. It was a performance graph, plotting horsepower against time. The curve climbed steadily to 2,000 horsepower and stayed there, flat and stable for 12 hours because, Heron said, "I've built the engine that's going to win the war." Henderson glanced at the graph. "This data is falsified. These numbers are impossible. The engine is in Hangar B. You can verify the data yourself, even if these numbers were accurate, which I don't believe. This engine is too heavy for current aircraft designs. It's useless. Then we build new aircraft designs? That's not how military procurement works, Mr. Heron. We don't design aircraft around engines. We design engines for aircraft. With respect, Colonel, that's exactly backwards. The engine determines everything: range, payload, altitude, survivability. Build the best engine possible, and the aircraft designs will follow. Build mediocre engines to fit existing aircraft, and you'll fight the next war with the capabilities of the last one." The debate continued for 3 hours. Heron presented test data, thermal analysis, metallurgical studies. The officers countered with regulations, procedures, budget constraints. It was an argument between 2 different conceptions of how innovation occurred. The official view, which held that progress came through careful planning and committee oversight, and Heron's view, which held that progress came from individuals willing to ignore the committees and build things that weren't supposed to be possible. In the end, it was not Heron's data that saved him. It was timing. On May 10, 5 days before the tribunal, Germany had launched its Western offensive. The Netherlands had fallen. Belgium was collapsing. France was reeling under the Panzer advance. The carefully planned defensive strategies, the static warfare that everyone had expected, had evaporated in days. Suddenly, the old certainties seemed less certain. Suddenly, the idea that American aircraft might be inadequate for the coming conflict seemed less like pessimism and more like realism. Henderson stared at the performance graph for a long moment. Then he looked at Heron. "If we authorize continuation of this project, will you follow proper protocols?" "I'll try." "That's not an acceptable answer. It's the only honest one. So the proper protocols are designed to prevent failure, but they also prevent success. Give me 6 months and a team, and I'll deliver an engine that produces 2,200 horsepower reliably. Make me submit every decision to a review committee, and I'll deliver a stack of approved paperwork and an engine that doesn't exist." Henderson's jaw tightened. Around the table, the other officers shifted uncomfortably. This was insubordination, clear and unambiguous. But it was also possibly true. 6 months, Henderson said finally. "You'll submit weekly progress reports. You'll coordinate with the aircraft design teams. And if this engine doesn't perform as you claim, I will personally ensure that you never work on a military project again." Heron nodded. "Understood." He left the conference room with his folder under his arm, walked across the base to Hangar B, and got back to work. The transformation in American aerial capability between 1940 and 1943 remains one of the most dramatic technological shifts in military history. In 1940, the most powerful American bomber engine produced 1,200 horsepower. By 1943, engines derived from Heron's unauthorized prototype were producing over 2,200 horsepower. This increase, nearly doubling engine power in 3 years, enabled aircraft designs that would have been physically impossible under the old constraints. The B-29 Superfortress, which entered service in 1944, carried 20,000 pounds of bombs across ranges exceeding 3,000 miles, operating at altitudes above 30,000 feet with pressurized crew compartments. It was not an evolution of existing aircraft. It was a completely new category of weapon, made possible by an engine that wasn't supposed to exist. But the significance went beyond raw performance numbers. Heron's engine introduced design philosophies that would reshape American engineering. It prioritized reliability over precision, maintainability over optimization, robust performance under imperfect conditions over peak performance under ideal conditions. These were not the values of peacetime engineering, which could afford to chase perfection. These were the values of wartime engineering, which had to chase effectiveness. German and Japanese engineers examining captured American engines struggled to understand this philosophy. They saw components that were good enough rather than perfect, manufacturing tolerances that were looser than their own standards. They interpreted this as sloppiness, as American industrial mediocrity. What they missed was that good enough components that could be mass-produced and field-repaired were strategically superior to perfect components that required specialized manufacturing and expert maintenance. The Americans had not lowered their standards. They had redefined what standards mattered. The symbolic object that came to represent this difference was not the engine itself, but something smaller, the spark plug. American spark plugs were simple, robust, designed to be replaced in minutes by mechanics with basic training. German spark plugs were precision instruments, beautifully machined, requiring careful installation and adjustment. In laboratory conditions, the German plugs performed slightly better. In combat conditions, in the hands of exhausted mechanics working in muddy fields at 3 in the morning. The American plugs meant the difference between an aircraft that flew the next mission and one that sat grounded awaiting specialized parts. This philosophy, this prioritization of practical effectiveness over theoretical perfection, appeared throughout American equipment. It was there in the looseness of tolerances that allowed mass production. It was there in the simplicity of field manuals written for conscripts rather than career specialists. It was there in the redundancy of systems, the interchangeability of parts. The assumption that things would break and need to be fixed under terrible conditions by frightened, tired people doing their best. It was, in a sense, a democratic approach to engineering. It assumed not genius but competence. It assumed not ideal conditions but reality. And in the massive industrial war that followed, these assumptions proved correct. By late 1943, Samuel Heron's name appeared on classified technical documents, on patent applications, on memoranda circulated among the highest levels of military planning. He had become, quietly and without public recognition, one of the most important technical contributors to the American war effort. His engine powered not just bombers but fighters, transports, even naval aircraft. Variants and derivatives proliferated, each optimized for specific applications, but all sharing the core design philosophy he had established in that freezing hangar in January 1940. Yet Heron himself remained largely unknown outside specialist circles. There were no magazine profiles, no newsreel footage, no public celebrations of his contribution. In part, this was deliberate. The capabilities of American aircraft engines were classified information, and publicizing Heron's work would have revealed technical details to adversaries. But in larger part, it was because Heron's story didn't fit the narratives that wartime propaganda preferred. He was not a hero who had followed orders and succeeded through courage and discipline. He was a stubborn eccentric who had violated orders and succeeded through obsession and insubordination. This was a truth more complicated than the simple stories a nation at war wanted to tell itself. The documented quotes from Heron during this period reveal a man largely indifferent to recognition. In a letter to a colleague dated December 1943, he wrote, "The engine runs. That is sufficient." In a memo responding to a suggestion that he receive a civilian medal, he wrote, "Unnecessary." The work continues. His focus remained technical, practical, obsessive. While others celebrated the victories his engines had enabled, Heron was redesigning cooling systems, testing new alloy compositions, pushing the performance envelope further. There is a photograph from early 1944 that captures something essential about him. It shows Heron standing beside a B-29, his hand resting on one of the massive engine nacelles. He's not looking at the camera. He's looking at the engine, his expression intent, critical, already identifying the next problem to solve. Behind him, ground crew members prepare the aircraft for a mission, but Heron seems unaware of them. In his universe, there is only the engine, the endless process of making it better. Japanese engineers who examined B-29 wreckage after combat engagements wrote detailed technical reports attempting to understand how these engines produced such power. They measured cylinder dimensions, analyzed alloy compositions, documented cooling system configurations. They reproduced the specifications exactly in their own designs, and yet their reproductions never quite matched the performance of the originals. Something was missing from their analysis. Some factor that couldn't be captured in measurements and specifications. What they missed was the philosophy embedded in 10,000 small design choices, the assumption that parts would wear and need replacement, the bias toward simplicity over elegance, the willingness to accept small inefficiencies in exchange for large robustness. These choices were not documented in the technical specifications. They existed in the accumulated wisdom of the engineers who had built the engines, in the field reports from mechanics who had maintained them, in the 1,000 small modifications and improvements that had occurred between the original design and the production versions. They existed, ultimately, in the stubbornness of one man who had refused to accept that certain things were impossible. The war ended in August 1945 with atomic fire over Japanese cities, a finale so overwhelming that it eclipsed the 1,000 smaller innovations that had made that ending possible. The B-29s that carried those atomic weapons flew on engines designed by Samuel Heron, but few who watched the newsreels made that connection. The engines were invisible, taken for granted, Just another piece of machinery that did what it was supposed to do. Heron continued working after the war, turning his attention to jet engines, to turboprops, to the next generation of propulsion systems. He published technical papers, advised on aerospace projects, accumulated patents. He died in 1963, his obituaries noting his contributions in language that made them sound incremental, evolutionary, the sort of steady progress that any competent engineer might have achieved. But those who knew the real story understood differently. In the archives at Wright-Patterson Air Force Base, there remains a file marked Heron S. Project Authorization Violations, 1940. It contains the original tribunal documents, the unauthorized requisition forms, the angry memos from supervisors whose materials had been diverted without permission. It contains, in other words, the evidence of what should have ended Heron's career. What would have ended his career if his gamble had failed. And clipped to the inside of that file is a handwritten note, undated, in handwriting identified as Colonel Henderson's. It reads, "Sometimes the regulations are wrong. Sometimes you need someone crazy enough to ignore them. There is a tendency, when examining history from a distance, to imagine that progress is inevitable, that the innovations that did occur were bound to occur, that capable people would have found solutions to the problems that needed solving. But this comfortable determinism dissolves when you look closely at specific moments. Specific decisions, specific people, standing in freezing hangars at 3 in the morning, deciding whether to follow orders or follow intuition. The engine Samuel Heron built in January 1940 was not inevitable. It required specific knowledge, specific obsession, specific willingness to risk everything on a belief that the official experts were wrong. A dozen different decisions, any one of which could have gone differently, separated the world where that engine existed from the world where it didn't. If Henderson had been less conflicted, more certain in his bureaucratic authority, Heron would have been court-martialed in May 1940, and the engine would have been dismantled, its innovative design scattered across forgotten technical reports. If Heron had been more reasonable, more willing to compromise, more cautious about risking his career, he would have submitted to the review process, and the engine would have been delayed, diluted, diminished into something conventional. The margin between success and failure, between the world that happened and the world that might have happened, was the width of one man's stubbornness. This is perhaps the real lesson of the impossible engine, not that American engineering was superior, not that democracy produces better weapons, not any of the comfortable ideological conclusions that might be drawn, but something simpler and more unsettling. Progress depends on people crazy enough to ignore the rules, and systems wise enough to tolerate them. It depends on the paradox of order and chaos, structure and rebellion, operating in tense, productive conflict. The German and Japanese engineers were not less capable than their American counterparts. They were not less intelligent, less dedicated, less innovative, but they worked within systems that punished deviation, that insisted on following established procedures, that treated insubordination as unforgivable regardless of results. When Heron violated protocol and succeeded, the American system, grudgingly and with great reluctance, made room for that success. When German or Japanese engineers violated protocol, regardless of whether they succeeded or failed, the system crushed them. This was not a difference in engineering capability. It was a difference in how much chaos the system could tolerate while still functioning. And in the desperate, improvisational conditions of total war, the ability to tolerate productive chaos turned out to be strategically decisive. On cold January mornings, when frost forms on the windows of the buildings that now occupy Wright Field, when the early light catches the ice crystals and makes them glow, you can almost imagine you see him, a figure in oil-stained work clothes, moving through the darkness toward a hangar that no longer exists, carrying tools and calculations and stubborn refusal. The hangar is gone. The engine is in museums now, behind velvet ropes. explained by placards that reduce years of obsession to 3 paragraphs of sanitized history. The men who worked beside him are gone. The pilots who flew aircraft powered by his engines are gone. The bureaucrats who tried to stop him are gone. But the engine still exists, not just in museums, but in philosophy, in the approach to problems that says the first answer, the safe answer, the approved answer is not always the right answer. It exists in every engineer who looks at official specifications and thinks, I can do better than this. It exists in every innovation that begins not with permission, but with the decision to build first and ask forgiveness later. The spark plug, that simple, robust, easily replaced component, became standard not just in American aircraft, but in aircraft worldwide. Today, somewhere, a mechanic is replacing 1 in 2 minutes, unaware that this simple act embodies a philosophy of engineering that helped win a war. The plug is unremarkable, ordinary, taken for granted, which is exactly the point. The greatest innovations are the ones that become invisible, that work so reliably and so consistently that people forget they were once considered impossible. Samuel Heron built an engine that shouldn't have existed, in defiance of orders, in violation of regulations, because he believed that the possible was larger than the approved. He was right. And somewhere in that cold January morning in 1940, in that moment when he tightened the final bolt and stepped back to look at what he had created, he changed not just the course of a war, but the possibilities of what engineering could be. The engine ran, and that, in the end, was sufficient.